Right. Hey, we are live for the fourth OpenMined State of the Community. We're going to try a new format today. So we've got a couple demos we've pre-recorded that we're going to show off for you. We've got, of course, Andrew and Andreas here. And Andrew, I think you've got some stats to open up.
Yeah, so it's been another great couple of weeks for the project, and we've passed 500 stars across our GitHub repositories. We're over 1,300 contributors on our Slack team. We were also featured on several Medium articles that did so well that they were also featured on kind of general medium.com pages, which was featured in Nathan Benoit's AI newsletter, which is one of the more prominent newsletters in the space, which is certainly an honor for the project. And yeah, so it's been a lot of great growth. And another side trend that I've also noticed is that I'm exceedingly grateful for is that the pull requests that we've been getting in the last couple of weeks have been truly deep. And clearly our community is starting to get a really great grasp of the core concepts of what we're trying to build, and really submitting some pretty substantial work. So great job, everybody, and very honored to be a part. I also wanted to at least mention the justification for this new change in format. So one of the things that was preventing some contributors from being able to submit demos for the State of the Community was just access to a high-speed internet connection to be able to kind of live stream, which requires a lot of bandwidth. So in order to make being able to show off your work and demo the functionality that you've added to the OpenMined ecosystem as accessible as possible, we wanted to instead switch to pre-recorded demos. So for the next time, if you build new functionality into OpenMined and you want to show it off to the community, put together a video demo that's 5 minutes long, and we'll include it in the segment that we're about to show you here. So there's some really great ones this week, and I'll pass it back to Patrick.
Yeah, right on. So we're going to dive into a couple demos, and we're just by the hair on our chinny chin chin, just trying to get this all to work. So if there's any technical difficulties, let us know, and we'll stop the stream, and then we'll upload the videos, link them to you, so you guys will get the demos regardless. But we're going to try this. So we're going to play some pre-recorded videos. Let's see.
Okay, welcome to my little presentation about the implementation of GPU support for the OpenMined PySwift library. A little bit about myself first. My name is Raphael Hohmann. I'm 20 years old. I'm studying bioinformatics at the Goethe University in Frankfurt, Germany. Okay, why do we need GPU support at OpenMined? First of all, deep learning is a really computationally expensive task. With a lot of matrix multiplications, it's dealing with really long arrays and a lot of mathematical operations on them. For example, gradient descent or activation functions. And we also have a lot of data to train on. So GPUs are made exactly for this because they are made for a high amount of floating point operations. Their hardware exactly fits our needs there. We also need GPU support because of homomorphic encryption, which is done faster on GPU. Since at OpenMined we're encrypting the user's data and the data scientist's model, it is convenient to do so on the faster GPU. And the biggest reason maybe is that every other big deep learning library also supports GPU operations. Okay, something about my thought process. I wanted to simplify GPU usage for the OpenMined project. And I do so by using OpenCL as a framework because it's platform independent, not like PyCUDA, which uses NVIDIA's CUDA and only supports NVIDIA GPUs, therefore. I also wanted to outsource computations with as few lines of code as possible. At the moment, we're around 2 to 3 lines, I don't exactly remember, per operation, which is pretty neat, I think. I also wanted to minimize the CPU-GPU data transfer bottleneck. I do so by using GPU buffers. Say we have a neural net, and after each training cycle, we have to transfer the net from the GPU back to the CPU and vice versa. You can imagine that this slows down the process tremendously. Okay, the current state of the implementation is that the OpenCL wrapper is nearly done. They're lacking some Efficiency tweaks here and there, mainly on the GPU-CPU bottleneck, but I'm currently working on them. Unfortunately, we only have a few kernels. A kernel is a mathematical operation you can perform on the CPU, or any operation. We're not going to dive too deep into that now. Yeah, we only have vector addition, I think, at the moment, and scalar multiplication. So we're just jumping right into the live demo. Okay, so we're here at PySift, Sift GPU core. The API has two main classes, which is firstly GPU core. The GPU core class connects the CPU to the GPU. It enables computations on the GPU, and they're on multiple working units, which are called GPU cores. That's where the name comes from. The other big object is the GPU buffer, which handles data transfer to the GPU and back. It essentially allocates memory to push data from the CPU to the GPU. Okay, let's jump right into our usage example. Here we're just importing GPU core simply because we need it. All right. So for my system, the GPU computation exceeds CPU computation at around 900,000 floating point operations. So we're just choosing a vector length of this size. Here we are creating NumPy arrays. You can use either NumPy arrays to put into core operations or GPU buffer objects, but more on that later. So now we are connecting to the GPU here. We are creating a GPU core object. So we are saying, we're telling the GPU that we should establish a connection to the CPU, and we're going to transfer data. So what we are doing here essentially is we are performing an operation, in quotes, on the GPU, because actually we are just enqueuing the operation, and we're performing it later. And we do so by using a method from the GPU core object. For this example, I chose to use vector addition, and this performs a vector addition of T1 and T2 on the GPU. Here we are receiving a GPU buffer object as an output. We are receiving a GPU buffer object as an output to use this buffer object as an input for another operation which can be run afterwards, like we do here. I didn't use a GPU buffer object here, but you could. And the reason is why we use a GPU buffer object here is to skip the GPU-CPU bottleneck, because this buffer object holds a pointer, in quotes, to the data allocated to on the GPU. And so we can use the result of this computation in further computations on the CPU. Okay, what I did here was just I defined a little benchmark function, and I defined the vector addition on the CPU. And what we do here is we're just benchmarking them. So here we use core.run. It's normally written like this because it's a method, but we pass it into a function, so we have to pass it by reference. Okay, so what does the core.run do? It runs all operations we specified earlier, we enqueued earlier on the GPU, and it manages also the data transfer to the GPU. So now we are comparing here the results of the first and the second computation, and I'm just going to run. Okay, now you see here that we run our function on the GPU for about 0.36 seconds, and on the CPU for about 0.37 seconds. And we see that the GPU was faster, and the results from the GPU and the CPU are the same. So everything works there. But we also have to realize that we ran two operations on the GPU. Meanwhile, we just ran one on the CPU. So we're practically double the speed there. And if we enlarge our data size by 100, we see that, we should see it. Maybe it was too big. Let's hope not so. Okay. On GPU, it ran 1.87 seconds. On the CPU, it's going to take a while. Sorry. Didn't test that before. Okay, I'm just going to stop it now, but you see that the GPU was faster than the CPU there. Okay, so a little resume here. We have to specify a core object. Then we can enqueue as many mathematical operations we want, or let's say as many mathematical operations that the GPU can handle. Then we run the core, and afterwards we can get the results by calling the out buffers, the GPU buffers dot result attribute. Okay, that was the little demonstration. It was a little bit long, sorry for that. Okay, what is the future state of the API? We need more kernels, for example, for activation functions, gradient descents, and so on. We also need to do some efficiency tweaks, mainly at the GPU-CPU bottleneck. And there are two big tasks we have to accomplish. The first task is multiple GPU distribution, which means that we can compute on multiple GPUs at the same time. And the second one is the support of encrypted deep learning computation. So we train encrypted data on encrypted models on the GPU. Okay, so that was it. Feel free to contact me if you have any further questions. My Slack is Ocean Coding, my Git is also Ocean Coding, and I'm pretty active in the Team PySwift channel. Until then, enjoy deep learning and have a great day.
Man, that was awesome.
Everybody, I'm Marco Bellan, an applied mathematics student from Milan in Italy. And what I do for OpenMined is work on polynomial approximations of activation functions. The reason we need them is because homomorphic encryption only works well with sums and multiplications, whereas it doesn't commute with respect to nonlinear functions. And here you can see an example. And what we need to do is implement some kind of nonlinear function, which is only composed of multiplications and sums. And in our case, polynomials do the trick. And so what we want to do is approximate the existing nonlinearities, such as 10H and ReLU, and even build new ones to make our networks work. And in order to facilitate the task, we built a really small utility in Swift.nonlin called polyfunction, which allows you to approximate a function calling polyfunction.fromApproximation and pass in the function you wish to approximate and some other parameters such as the interval of approximation, and you will get the approximated polynomial back. And you can evaluate such polynomial and see the value it takes. And you can calculate its derivative, which is calculated starting from the fitted polynomial. What you can also do is pass in the derivative of the function itself. And so we will do polynomial fitting both on the function and its derivative. And we find this approach to be more precise. You can evaluate both, and you can see the values are slightly different. And we can try and plot the functions, the red one being the original and the blue being the approximation. And if you plot the derivatives, you can see the green derivative is actually quite off, whereas the one calculated with fitting, which is the blue, is very, very close to the red one, which is the original. What you can also do is change the node distributions, which are the points on which the polynomial is calculated and built from. You can use both uniform and Chebyshev, which works better with higher degrees and prevents the Runge phenomena. And you can try and plot them, and you can see the results. The blue and the green one are slightly different, but it's not really noticeable with our degrees. And one thing to keep in mind is that interpolation always happens on an interval. So if you try and pick some data points and evaluate the polynomial outside of that interval, then you will see the original function and the polynomial start diverging. So it's really important to make sure that you've got a quality approximation that behaves well and doesn't diverge too much. And in order to make sure this is the case, we're carrying out a lot of tests using Keras and some sample models. For instance, we're working on the means dataset, and we built a control model using a ReLU activation function. And you can see the accuracy increasing with time and the loss going down. And the same network using a polynomial activation, in this case y equals x squared plus x, converge quite well. And we can say the same for the y equals x cubed case. And if we plot the convergence, the validation accuracy in this case, you can see that the red one, being the ReLU, is actually lower compared to the blue one, which is our square function. And this is really promising. And so we want to carry out more tests on bigger data sets and different domains, such as natural language processing. And we'll let you know how they go. Eventually, we want to start using those activation functions outside tests. And as such, we'll need an activation class for Swift as well. And you can find them in Swift.nonlin. You can find some ready-made functions approximations, such as sigmoid. You can calculate both the value and its derivative. Square, linear square, which is the one used in the test I showed you before. Cubic. And you can also feed a custom function with the dot from approximation function I showed you before and pass it to a polynomial activation. And you can evaluate it and its derivative as well. One thing we need to make sure is that the polynomials are calculated efficiently and in a stable manner. And we want to pay attention to the noise growth, which is a really big issue with homomorphic encryption. And as such, we need optimal algorithms that do as least multiplication as possible. And that's about it. If you're interested in helping us out, then write me at Marco Bellan on Slack.
Right on. Well, I hope that worked. See, Andrew.
Great.
Yeah, did that work?
And great job both to Ocean Coding and to Marco. Like that was those were absolutely fantastic demos, and I think it really captures the level of depth that our community is starting to reach to. And yeah, please do reach out to them if you're interested in collaborating on those projects.
Yeah. I would like to give a quick demo of something I've been working on. Actually, Andrew, this is a little unscripted. I said I wouldn't go into, but I am. So I've been working a little bit on a design for our Mine library, Mine UI, which is Mine.js. Yeah, I know. And so it's all totally temporary. I've got it wired up in Envision app, which is just a little clickable demo. So. But the basic idea, I mean, you would have a user interface where you're able to track what data has been requested by the Sonar model. There's this concept in the adapter proposal as to whether or not a model would be public or private, as well as the total bounty, how much time is remaining, whether or not you want to pause training. There's also a possibility in the future, and Andrew, I'd love for you to talk about the next Helium milestone when we're done here, but one thing that wouldn't necessarily be included would be this concept of auto-enrollment, to where basically you can set it and forget it. So any Sonar models that exist that you have the data for, you would be able to auto-enroll, and it would just start training them in your sleep. So you wouldn't actually have to actively click on models to train. Here's the concept behind the general schema. If any of this, again, looks unfamiliar to people, please check out the adapter proposal that we've put together in the Team Adapters channel. But here you'd be able to go through and define all your information. You can also see that some information is not input at all, but it's directly being pulled from, you know, various third-party adapters. You also see right here with employment, we've got one to where LinkedIn is pulling in 6 jobs that we've got listed, and then we've also got one that we've manually entered that's not visible on LinkedIn. So that shows the combination between doing manual entry on the general schema as well as pulling in connections. I'll be working a lot more on the UI of this. It's nowhere near ready, but I'll be working a lot more on that over the coming days, as well as beefing out the adapter specification to make sure that we're headed in direction with that. Some example ways in which adapters would work. Of course, you've got your adapters currently in use here. You can add a new one if you want. You can click on Twitter. This would provide you instructions. There is some discussion as to whether or not these would inevitably be OAuth endpoints. That would make sense, so you're not having to upload your data every single time you make a new tweet or a new Facebook post. That would be ridiculous. But for the time being, for some potentially legal concerns, we're maybe not going in the OAuth direction quite yet, but that is in the pipeline. For now, though, you would do something like just request your archive. They send it to your email. Right here, you would upload your data. And then actually the adapter's job is to parse out what information is available in that upload. You can optionally say, I don't want to overwrite anything in my profile. I've already got that filled out well. I don't need any location data that Twitter gives me. I'll just pull in my screen name from Twitter and all of my posts. You can import them. And then at that point, you'll have to call through and determine all the duplicates. In this case, there were none, but there may be duplicates, for instance, from previous data that you've uploaded. You want to make sure that all of the data you're uploading to your mine, to your general schema, is consistent and that there's not duplication anywhere. So that's something I need to hash out a good bit more. I'd love some help on that from anyone in the community, especially any user experience people. So, and again, back to your general schema. You can view your previous bounties, so on and so forth. Again, everything is in dollars in the mockup. That could be Ethereum, that could be whatever cryptocurrency you prefer. But that is the gist of it. So it's a work in progress, but we're getting there. So
that's awesome. Great job, dude.
Yeah. Well, cool. Andrew, if you got anything else, I'm good.
Yeah. The only thing I would add is in the midst of trying to figure out what we want to push for in the Helium milestone, and I think jumping on those conversations, it's looking like it's going to focus on a specific demo backing functionality that Patrick was just talking about, and with the hopes that we can actually get up onto a test blockchain on Tendermint and Ethereum, and I think that's a very exciting milestone for us all, and I look forward to getting there. So we've got lots of great progress and lots of great tickets to both create and knock out between now and then. But yeah, other than that, very excited.
Andreas is super stoked about it. Cool. All right. Well, if that's it, guys, then I think we'll call it. But thanks everyone for tuning in. Appreciate it.
See ya.